So yeah, today we're going to talk about a crazy hobby project of mine that has derailed all sorts of my work. But first, the atomic bomb. In the 1940s, a group of American scientists got together and designed and built the world's first nuclear weapon, the first atomic bomb. And while I personally don't approve of the outcome of that research, it was an incredible scientific achievement, and they overcame many, many obstacles in order to successfully deploy the weapon. And one of the biggest obstacles was called the nuclear diffusion problem, right? And the idea is that when you create a nuclear reaction, all these particles are moving around in extremely chaotic ways that are determined by subatomic interactions, right? You have especially neutrons that need to be controlled in the reaction if you want a weapon that you can actually, basically a weapon that you can deploy when you want to and not accidentally, and a weapon that once you deploy it, the explosion happens in the shape that you want it to happen. So that was called the neutron diffusion problem. And it turns out that the set of variables that go into where a neutron moves, how neutrons scatter in a reaction, it's just incredibly hard to compute. There's so many variables, so many inputs, and so many possible outcomes of this chaotic system that they were stuck. They couldn't come up with a model for solving it. So instead, what they did with the limited computing power of the day is they started inputting random values into the variables that determine the result of the explosion, and then plotting where the neutrons would have moved if those were the initial values. And they did this mostly by hand, thousands and thousands of times, plotting each value, and eventually, amongst the chaos, patterns emerged. So they couldn't tell with certainty exactly how the neutrons were going to behave, but they could give you a heuristic. They could say, well, it's most likely that neutrons are going to cluster in this direction if we build it like this. So they built this statistical model that was based on inputting completely random numbers into a system, and because of that, they called it Monte Carlo integration. They named it after the Monte Carlo casino, right? Where you just put it all on black. So 40 years later, a computer scientist named James Kagia was working on more realistic computer graphics. And he looked back into historical research, and he found Monte Carlo integration, and he turned it. Instead of using it to determine how neutrons would explode in the blast radius of a nuclear weapon, instead of predicting where neutrons would go, he decided to predict where photons would go, and use Monte Carlo to predict the movement of light amongst a scene. And so he repurposed this 4 decades later, and he published a paper called simply the rendering equation. And it's an equation that if you can solve it, it's an infinite integral, and if you can solve the equation, or if you can approximate the equation even, you can create an image that is so close to reality, that's so close to a photograph, that it's indistinguishable from a photograph. It's a photorealistic image. Now, at the time, computing resources were so limited that this was mostly an academic exercise. This is an image directly from his original paper. And it was smaller than this. I had to blow it up, right? The resolution is tiny. The scene is a single sphere on a single plane. The materials are pretty basic and uninformed by today's standards, right? So at the time, you couldn't really take advantage of the rendering equation, but Kagia proved that if you had the computing resources that maybe we have today, that you could fake images with absolute clarity so that a human can't distinguish them from reality. So then 10 years later, Toy Story changed the world. It was an influential film in my life when I was a kid. I wanted to be a 3D animator for a long time. I loved this movie. And when it came out, it was the first feature-length film that was entirely animated inside of a computer. Nothing but a simulation. There were no real props in this movie for the first time. Steve Jobs was very proud of the fact that there were more PhDs working on it than on any other movie in history. And this is an interesting point because for the first time, engineering as a discipline was just as important as artistry or acting to the success of a film. Damn it. It took $30 million to produce Toy Story 1. And Steve Jobs said that if it made $100 million, that he and Disney were both going to make a lot of money. And if it made $200 million, that they were both going to make a lot of money. And it ended up making $364 million, proving that there was a market for 3D films that were rendered entirely inside of a computer. But despite all of his PhDs, Toy Story still did not use the rendering equation. In 1995, they just didn't have the computing resources to actually compute that integral. So instead, they had a bunch of artists manually placing things they called bounce lights and shadows to try to fake it, to try to make it look like there was light bouncing around the scene when there really wasn't. So then in 2006, Monster House came out. It was released by Steven Spielberg, and it wasn't the commercial success that Toy Story was, but it was a technological success because it was the first movie that from end to end feature-length film used the rendering equation to render all of its scenes. So a physically based path tracer integrated Kaguya's rendering equation to render all of Monster House. So at this point, we knew two things. By 2006, we knew that it was economically profitable to build 3D simulated movies inside of computers. And we also knew that it was computationally feasible to make them. And then, secretly, Disney started working on their own global illumination renderer sometime around 2011. It was called Hyperion, and they unveiled it to the world in 2014 when they released Big Hero 6, which was the movie that they made it for. And Big Hero 6 overcame a lot of the challenges that you had seen before with the rendering equation because they had so many more compute resources than anybody ever did before. So when they rendered Big Hero 6, they used 4 render farms. 3 of them were in Los Angeles, and 1 of them was in San Francisco. Across those farms, there were 4,600 servers, and an average frame took 83 hours to render. Yeah. I'm going to quote this. I hope I remember the fact right, but I think they said something like it could have rendered Frozen in like 10 days or something like that, like the whole thing. And by the way, it took 2 years to make Big Hero 6. So even with modern technology, this still is computationally expensive work. Who saw Deadpool in 2016? Yeah, basically everybody, fantastic. Did you know that the first minute and a half of the movie did not exist? It was entirely rendered inside of a computer. All the actors, all the people, all the vehicles, all the props, all the bullets, literally everything, all the scenery didn't exist. The first 90 seconds of Deadpool was completely digital. This frame, there's no person there. That is a 3D model. This is rendered in, this is just a figment of a computer's imagination. It's all path traced with the rendering equation. And in 2016, things got so good that Pixar decided to go all in, right? We're only going to do path tracing from now on. So their proprietary renderer, RenderMan, they got rid of all the old legacy stuff that they used for things like Toy Story, and now it only does path tracing rendering based on this rendering equation. If you've seen any of these movies, then you've been privy to the graphics that are possible when you combine the rendering equation with Monte Carlo integration with path tracing. This one in the lower left is really cool because there are actually no actors in that scene. They 3D scanned the actress and purely animated everything. There's actually no person there. It's just a 3D model of her. And what's really neat about all these movies is that they can trace their mathematical roots back to foundational principles that were developed when we were building the atom bomb, which is just very weird to me. So they all have the same lineage, and it's all to war. So late 2016, Disney published this, and somebody linked me to it. And it's really lucky for them that I can't remember who they were, because I would send them a bill for the hundreds and hundreds of hours that I spent just completely derailed from my normal work. I mean, I build network services at Heroku. This is not my normal thing, but it just was so fascinating. I saw this, and they explained path tracing in a really accessible way. The gist is that you have a scene and you have a light. And that light just shoots light rays out into the scene, and then those light rays bounce off of objects. And every time they bounce, they lose a little bit of energy. And so objects illuminate each other. It's not just light to objects, it's objects to objects as well. They're like, so if you stick a camera in that scene, some of those rays are going to go into that virtual camera. And if you record how bright they are when they go in, well, then you render an image. But as you can imagine, 99.9999999% of all the rays don't make it into the camera. So what's the trick? Well, the trick is instead of shooting light rays from the light and letting them bounce into the camera, you just make it go in reverse, because light is bidirectional. If you bounce light from the right or the left, it doesn't really matter. It'll follow the same path lose the same energy. So now you shoot the rays out of the camera into the scene, and then eventually they find a light, and based on all the bounces that happen between them, that gives the light ray its color, and now you know what the scene looks like. You've illuminated the scene. And what's really crazy is that this is the whole algorithm. Like, this is it. This is actual working Go code for a grayscale path tracer. It will render an image. You have to implement a couple of things, like the intersect function, and you have to have objects in your scene. But this is all it takes. And when I saw this, I was like, holy shit, I have got to build one of these. Right? I mean, I can't not do it if it's this easy. So a couple of things to notice is it's just a function that takes a ray, and then how many times you want that ray to bounce. Once you run out of bounces, you just return black, which means no energy. We didn't get any light here. You try to intersect the ray with something in the scene. If you don't intersect it, again, no energy, right? It just went out into space. There's nothing in space. If it hits a light, you just return the light, right? If I look directly at a light, if I photograph a light, it's just going to be the brightness of the light. Otherwise, you bounce it. And this is the crazy part. This is where Monte Carlo comes in. You just send it in a random direction, right? You just literally say, all right, now bounce it in some random direction. And then it's a recursive algorithm. So you call trace again with one fewer bounce. You add the reflectance of the object it bounced off of. So like something that's white might have a reflectance near 1. Something that's black might have a reflectance near 0. And all that shows is how much energy is lost in that bounce. And this is a path tracer. This is a working path tracer. That's all it takes. It'll be slow as hell, but it'll work. So I saw all this. I kind of went through all this in like one day at a cafe. I remember because my wife actually came in a few hours later when I had gotten my first version working. And she was like, what are you doing? What are you working on? You seem very excited about this. And I told her, I was like, holy shit, I just implemented Pixar's algorithm in an afternoon, right? I can render things just like Disney, just like Pixar, just like Blue Sky. And she's like, oh, that sounds awesome. Well, show me. I was like, all right, get ready. Here we go. Bam! Right? So she's like, all right, so you drew a circle. I was like, a circle? This is not a circle. This is a glowing sphere, right? Because there's a sphere, and it's a light, and there's a camera, and that's what we're viewing through. And this camera is sending out hundreds of thousands of rays into this scene. And when the rays don't hit anything, they just return black. And when they hit the light, they send that information back. And then I plot the color of the light on the canvas, and boom, and now you have a glowing ball of light right there, millions of rays later, right? She's like, that's really impressive, honey, real impressive. And she's very supportive in everything I do, so whenever she acts like that, I'm like, I need to make this cooler, right? I have to keep working on this until she's really impressed. So I decided to go a little bit past Disney's intro to rendering and the Wikipedia article with that pseudocode. But I ran into 2 obstacles that Disney had not prepared me for. The first was math, right? I don't know how to pronounce any of this. I don't know what these symbols are. I don't have a math degree. And as soon as you start getting into rendering, you just see pages and pages of papers like this. Like, this is what it all is. This is what academia is all about. And I chose this one in particular because I thought this guy was particularly cheeky for calling it basic. So that's the first problem. The second problem is, and this is I'm coming clean to you guys. All right, so for the first 3 years I worked at Heroku, I was the Node.js platform owner. I was the JavaScript guy at Heroku. So my sort of like native language is JavaScript. Now I'm the engineering manager of the languages team. I'm branching out to other things. But at the time, JavaScript was the most familiar to me. So I wrote the first version of this in JavaScript. And this image with like 5 spheres and a couple lights and it's like really low res took 4 hours to render, right? And when you're trying to figure out this complicated math that you just don't really understand, when you have a feedback loop of 4 hours before you know whether you did it right or wrong, it does not accelerate the learning process. Let's just say that. So at Heroku, we have all sorts of Go experts, which I found convenient because then I was like, fuck it, it's time to learn Go. Right? Like, I want this project. I'm so excited about this project. I want to keep moving. So this rendering is the reason that I even dove into the language. So, oh yeah, this is a reminder to myself that I want to start doing a live demo. So as you saw, it takes 83 hours to render a frame of a movie. A live demo is a bit of a misnomer there. So we are going to, I prepared a thing that I'm going to start right now. Can you guys see that at all? No, you're not seeing that screen. Give me 1 second. I want to prove to you that this is, in fact, a live demo. Can you see that? Yes, you can. All right, excellent. So I'm just going to make a Gopher. All right, this is going to run. This is the little Go program, and it's going to do its thing. All right, so I'm going to let it keep on rendering while we keep going, and then I'll show you what it looks like right now, though. At a really early render, we can open the Gopher early on, and I'll bring that over to the other screen. You can kind of see, like, he's a fuzzy, like, kind of pixelated Gopher. He's not beautiful yet. But this is how the render will start, and we'll check back on him at the end of the presentation. All right. So now, we're making a Gopher. Let's talk about building a path tracer with Go that takes less than 4 hours to render things. We're going to talk about it in plain English with just the tiniest bit of math and a touch of physics. I promise. Like, that's it. That's all we're going to do. There's not going to be any rendering equations anymore. And actually, the code that you've already seen is the most code that's going to be in the rest of the talk. So the first question I have for you is, what is light? It's kind of philosophical. What is light? I learned so much about light when I was building this. It's amazing. I'm going to share some of it with you, whether you want it or not. So light has a lot of properties. It's a wave, but it's also a particle, right? Light represents energy on some spectrum. It can be the visible spectrum. It can be ultraviolet. It can be infrared. Light can be polarized, so its wave can move along just a particular axis. But as a graphics programmer, you usually care most about 3 properties of light. Light has an origin, it has a direction, and it carries energy from that origin along that direction. Usually that energy is represented by RGB values. So that's how you generally represent light in graphics. And this is kind of what that might look like in Go. And this is how it looks like in my little implementation in Go. It's just a pretty simple vector 3. So then the next question, what happens when light hits a surface? When these lights are hitting this surface, what are they doing? Well, it's interesting because no matter what kind of light it is, no matter what shape of surface, and no matter what that surface is made out of, there are only 2 things that light ever does when it hits a surface, whether it's glass or metal or plastic or anything. It either reflects off of it without really changing much, without really losing or gaining any energy, or it refracts inside the surface. So, people say, oh, well, light bounces off of, objects and it loses energy and that's color. That's horseshit. It actually goes inside of the material, and that's how it loses color. Except for metals. Metals, or conductors, they don't refract, they only reflect. So whenever you see anything that's metal, you're only seeing reflections off of the surface. And the reason that metals, unlike anything else, can actually change the color of reflected light a little bit, like if you've ever seen gold, it's obviously changing the color a little bit, is because metals interact with light because it's an electromagnetic wave. So metals, unlike all other objects, can change light that doesn't interact with them in a physical, under the surface way. Nonmetals can do whatever, right? They reflect, but they also refract. And the biggest thing that determines what a nonmetal looks like when it's refracting, when the light is going inside of the surface, is how far into the material does the light go before it hits a particle of the material. Because when it hits a particle, then it just goes crazy. It scatters in completely unpredictable random ways. So different materials interact with light in different ways, and the biggest way is how far through that material light can go. So both of these cups are pretty much the same. The only difference between them, the single difference that makes them look so different, is that the material on the left allows light to go through it more before it hits particles, and the one on the right doesn't. You go a nanometer in or whatever, and it hits and then diffuses in random ways, and it looks like it's bouncing off the surface. So the model that is used in physically based rendering is that all light either ends up being reflected, diffused, or transmitted. Basically, all incoming light has to do one of these things because of conservation of energy. So it's our job as programmers to figure out which one it is. How can we simulate these 3 behaviors with Go? Well, that's where this comes in. Bidirectional reflectance distribution functions. When I read that, I was like, I got to take a break today. This is ridiculous, right? And then I found out what it is, and I was like, Jesus, can these academics not just give something a simple name? Right? Because this is actually maybe the simplest idea in this whole talk with the longest acronym. And here's the idea. It's a pure function that describes a material. It takes two arguments. Those arguments can be flipped. That's one of the properties of this, because it's bidirectional. One of the arguments is the incoming angle. Is this a laser? Oh, cool. All right. The incoming angle, and the other argument is the outcoming angle. And then the result of this function is what percentage of the light is allowed to continue in the outgoing direction. That's it. So maybe you attenuate light by 50%, so then you would return 0.5 or whatever, right? That's literally all it does. But this function is what determines the look and feel of a material. Like, this is a very, very simple material. This would kind of look like chalk, but like perfect chalk. The most perfect chalk you've ever seen. So this is like the simplest BRDF you can make. But the good news for us, as graphics developers, not physicists, is that people have already done all the physics. So if you're trying to make something that imitates realistic materials, you don't have to invent your own BRDFs. All you have to do is understand what a BRDF is. It's a pure function that takes two angles and returns some value between 0 and 1, because you can't reflect more light than you take in. And you have to read a bunch of papers like the microfacet BRDF model and Oren Nayar and all this stuff, and then translate their crazy gobbledygook math into Go. And it's really cool because all these companies, Disney and Pixar, et cetera, publish stuff like car paint, hair, thin films, clouds, all the ways that they render their movies. There are papers out there about it, just waiting to be implemented. So if you ever did statistics, more than I did, you might be thinking, but that's just one random path. We literally just chose a random direction and traced like one path from the camera. Is that not just going to be this crazy image that's just noise, that's basically just a random number generator like splatted onto the screen? And that's a very valid question. And that is where Monte Carlo integration comes in. And it took me a long time to figure out what all of these symbols meant. But essentially, it's this. I'm going to skip straight to the answer for you people so you don't have to figure it out too. Monte Carlo integration means sample a bunch of values randomly, add them all up, and average them. And that's probably close to the real answer. That's literally all it means. So that's what we're going to do, right? So when you combine path tracing, Monte Carlo integration, and the rendering equation, you start to get images that look like this. This is an image after like 1 second of running, right? And you can see the noise in here. You can see that we're kind of guessing at where this light is going to bounce. We're making some educated guesses. There's some things you can do there where you try to say, well, this is a very reflective surface, so I'm going to guess a little bit smarter, and it's going to bounce off a little bit more at a glancing angle. But in general, we're still guessing, and you can see the error in our guesses here. But if you let it render for another 30 seconds, you get something that's a little bit closer to something you could call a photograph. And if you let it render for like 5 minutes, you get something that's really close to the actual answer to the rendering equation. And this is something that's actually rendered with PBR in Go, right? So this, you can go get it right now, and I think it's like make shapes, and it'll render this on your machine. This was the point of departure from the JavaScript implementation. It was actually a little bit behind, but this is as close as I could possibly get, like a one-to-one comparison. People ask me, how much faster was Go? And man, it's hard to say, but this is, I was still doing simple shapes at this point, and it was about 15 times faster than JavaScript at this point. So something that Go could do in a few minutes, JavaScript would do in a few hours, basically. Okay, so we're making all these, spheres and boxes and whatever. But how do we make more interesting images with our Go-based path tracer? Let me make sure I've got, oh yeah, I've got plenty of time. That's great. Okay, cool. So how can we make more interesting images with our Go-based path tracer? First, we can give it complex geometry. And in the real world, not in the real world, in the world of rendering 3D things, and production 3D rendering world, most objects are described as triangles, just hundreds of thousands of triangles. This car is just a bunch of triangles. And most of these things come in standard formats. In this case, PBR currently supports the object format, which is one of the simplest and most popular. It's literally just a text file that just like lists triangles. It's super basic. All right, so now we can render complex geometry. what might we want to do next for interesting images? What if we made physically based materials? What if we tried to make real gold or real glass or, or real Coke bottle glass and stuff like that? Well, like I said earlier, the physicists have done all the work for us. All we have to do is translate their equations into Go. And so we can just take things that already exist that have been measured from real materials and then just, kind of write Go-based wrappers around that math to make physically based materials. And then this last method of making more interesting images is maybe my favorite because it's the easiest. It is just the simplest thing. It's a one-line change in your program, but it really helps the results, and that is image-based lighting. You can take the same model with the same textures and the same materials and render that model in different environments, and suddenly you notice the impact of the environmental lighting on that texture surface. And when I saw how to do this, I was like, God, that seems like cheating. But it's literally just, you replace the one line, right, where you would normally be like, oh, if I didn't hit anything, return black. You just say, if I didn't hit anything, return whatever pixel the background color is. And then it works. It just magically works. It's very cool. So those three things let you make more interesting images. And that's kind of where we are right now. But what about the future? I talked up until recent movies like Wonder Woman and stuff, but what about the future of physically based, path-traced images and videos? 2018 is actually a really interesting year for this. I didn't expect this to happen before the talk. This all happened between when I proposed it and now, actually, but every major hardware and software vendor has announced support for hardware-accelerated GPU ray tracing. Right, so Microsoft is providing the software layer with DirectX. NVIDIA and AMD are providing the GPUs that will actually trace the paths of rays on a GPU by default. Unreal Engine and Unity are both providing support for this. So the industry is starting to realize that, we are getting to a point where commercial hardware, or just standard commodity hardware like a home computer, can actually render these things in a reasonable amount of time, which is totally crazy to think about because when this equation came out, it was, 30 years ago? And the person that wrote it during that time, during decades later, never actually got to experience what it would look like. And we can today on a laptop. It's crazy. And it's an exciting emerging field, and I wanted to bring it to the attention of Go developers because there's mountains of research that nobody has implemented yet, right? That's just somebody's doctoral thesis somewhere. It's an embarrassingly parallel algorithm, right? You notice that we didn't do a whole lot of state changes here, and the more samples you have, the better. So you can just keep on resampling the same pixel over and over, and the more samples you have, the closer you're going to be to the real result. So there is no penalty to just throwing concurrency at this problem and just sampling it as much as possible and then taking every answer you get and just stacking them on top of each other and then just adding the result and then averaging by the number of samples. It's a fantastic, embarrassingly parallel problem both for local concurrency and distributed concurrency. And it's currently dominated by C++ programmers. And I've been talking to a lot of actual experts in graphics over the last year as I've kind of gone down this rabbit hole. And one of the things that they've told me is that the community is getting a little frustrated with how C++ every year becomes more complex than the previous year. And they're starting to look outside of C++ to see what might be there. Now, one big obstacle for the Go community is our garbage collector, because they're all about performance and graphics. A lot of them are looking at Rust. But I wonder sometimes if maybe a beautiful and simple concurrency story, now that Moore's law isn't really holding up anymore, could compensate for the fact that Rust might be able to edge out a little bit of extra performance in comparison to something that has a garbage collector. This is a really interesting field to get into. And then here is my shameless plug. I want more people to help me with this really pointless hobby project. And I sneakily inserted a primer and everything you need to know to be a contributor to this during this talk. Right? So at this point, you know everything you need to know to help me with at least one of these problems. Yeah. So I expect to see some pull requests or at least issues open soon. Come on. And there's some really interesting problems in this space. Distributed concurrency is something that Go should I have no excuse. I'm going to have to go back to my boss and explain to him that I didn't have time to build this into the demo. But I work at Heroku. We have oceans of servers, and this is a Go program, and I didn't build a distributed concurrency demo. I'm so sorry I failed you all, right? But this needs to be in here. New file types, bump maps, video instead of static things, participating media like clouds, subsurface scattering to render skin and like the blood vessels under skin, as creepy as that sounds. More performance. I'm sure I could use a lot of help there because I'm not a Go expert. GPU support, beautiful example scenes. So if any of this sounds interesting to you, please, I would love to hack on this with other people. Give me an excuse to keep working on this, please. And now, let's check on our Gopher and see if he has resolved any. All right. Oh, look at that guy. Right? Yeah. I'm pretty happy with that, right? Yeah. I'll have to make a pink version for the toys that they're giving out today. Guys, I really appreciate your attention, especially late in the day after many talks, although they were all really cool. And thank you to our hosts. And I'll be around for talking about this all night tonight, tomorrow. I'm going on that community thing on Sunday. I would love to talk to anybody about this stuff over a beer or whatever. And thank you for your attention. I hope you enjoy the rest of the conference.